Rod Brooks is one of these guys who doesn't need much introduction, but I'm going to give him one anyway. He is the founder and CEO of Rethink Robotics, which is really trying to disrupt the automation industry. Prior to that, he did a number of things, including bringing the Roomba to a lot of our homes. He was the founder and ran iRobot for a while, bringing robots to a lot of domains where they had no previous history, including the floors of our houses. He was the director of the CSAIL, the Computer Science and AI Lab at MIT for a long time, was featured in the Errol Morris documentary, Fast, Cheap, and Out of Control. Again, I need to stop reading the CV, not because I've run out of highlights, but because we need to move on to the actual talk. Rod is one of the institutions of the Institute, and we are tremendously happy to have him here. My personal thrill is that I've heard Rod talk a couple different times. He says this is a brand new talk that he's trying out on us. I cannot wait to hear what he has to say. Rod, over to you.
Thanks very much, and thank you for being here for this. Thank you for inviting me. Earlier, I think it was Andrew asked, who here feels that there are an admissions mistake at MIT. Well, I applied and didn't get in, but I'm not bitter. And I applied for a faculty job 3 times and went through the interview process 3 separate years before I got in. So it takes me a while to get things right. And as Andrew said, this is the first time out with this talk. So I'm sorry you're guinea pigs on this. It'll get better the next time, I hope. So I've been doing manufacturing for a long time now of different things. And I noticed a couple of trends. One is on the left there, what happened chasing low-cost labor. Right after the Second World War, we moved low-cost stuff to Japan, standard of living went up, we moved to South Korea, we moved to Taiwan, we moved into southern China, and even by the late 90s, some things were too expensive to do in China, you had to move down to Vietnam, and then you run into Thailand and Malaysia, which have been industrialized themselves. So we're running out of room for low-cost labor. We just had the peak 19-year-old year in China. The number of 19-year-olds is going down, and that's where the labor comes from in China. In the US, though, we've gone to large-scale manufacturing of expensive goods with automation. It's high capital investment, and we've increased productivity in US manufacturing by an average of 3.7% for 60 years, which has meant some of the things that Eric and Andrew talk about the number of employees finally going down because of that increase in productivity. But we haven't been manufacturing the ordinary stuff that we all use every day. Now, there's a movement going on called the Maker Movement. And Andrew, I put up the Maker Fair at Orlando. The biggest one is in San Mateo, but I know that you love Orlando so much that even in Orlando, the Maker Movement is happening. It's happening all over the country. And in the middle, at the top there, you see a MakerBot, which is a 3D printer from a New York company for about $2,000. It's made of wood, but it's a 3D printer. So all these people are playing around with trying to build stuff, custom stuff, get information technology down to the building level, using the Arduino systems for all sorts of things. A lot of experimentation going on. And my question is this going to lead to something big, something different? And I think a lot of people are wondering about that. And I think I've got 2 data points. I've got the first industrial revolution and the second industrial revolution. So I put a straight line between those data points and got the third one. Maybe that's why it was so hard to get a faculty job, I'm not sure. But the first industrial revolution was mass production through exploitation of non-human energy. You had steam engines providing energy, and you had belts and things, and you brought it down, and you manufactured stuff. That happened in England in 1780. Then in the Boston area in 1900, we got electrification. Actually, electrification first came to factories as the only app for electricity was light bulbs. And in the building that I'm in South Boston, it had a generator in 1895 for 16,000 light bulbs. That was how you measured electricity. Manufacturers came in, rented floors, and then they realized they could start to use the electricity for the manufacturing process. And so now you didn't have to have, eventually, the source of energy where you're doing the manufacturing. So that's what I call the second revolution. And the third one is allowing the workers to control the production themselves. It sounds a little like Carl may have said it, but I really think there's an empowering that's going to happen. And we've seen an analogy of that. So the question is, there's a Course 6 graduate on the cover of Wired, Lemore Freed. Someone said earlier on, the innovation doesn't happen in Minneapolis, but there's a hack factory in Minneapolis. People are out there hacking, building stuff. Can this stuff ever grow to replace China? Or is this just too hobby-ish? And I go back to something that happened right here in Silicon Valley, the Homebrew Computer Club. And I was around when this was happening. And it was a bunch of crazies and misfits that were doing weird stuff. I remember on my bicycle in Palo Alto in 1977, riding past a store which had a mainframe in there that you could go and program. Ordinary people could go and do it. I thought that was a little quirky. I've been programming 360s and PDB-10s and stuff, but ordinary people could just go in there and program stuff. It was sort of weird, but out of that came the stuff on the right. Out of that came our information revolution. That is that's why all of you live here, because of that Homebrew Computer Club. So it was quirky, it was little, but it led to this tremendous industry. Can anything like that happen with manufacturing? Can we get, we're not going to be manufacturing forever and ever in China. It's not going to look like it does now 500 years from now. It's not going to look like it does now 50 years. It's not going to look like it does now 10 years from now. So can we get there from here? And I think there's three questions to ask. To get there, what do we still need to invent? What infrastructure do we need to grow? And what new business models need to emerge? And I'm better at the invention stuff. Some of you, I hope, from Sloan are better at the business model stuff, and the infrastructure stuff has sort of sandwiched in the middle. But I'll talk about this a little bit. Software, digital, is the answer. Digital is what is going to enable all this. I'm going to give you an example of those three things: invention, infrastructure, and business models with a place called MFG.com. Does anyone know MFG.com here? Have you used it? Anyone use their services? Okay, you're not many Course 6 graduates then. Course 6 graduates use their services, even at MIT, to build prototype stuff. This just like, by the way, MakerBot, MFG.com, and my company, Rethink Robotics, have a common theme, and that is early investor Jeff Bezos. Interesting commonality there. So MFG.com is a marketplace for buying low-volume stuff. And I happen to have here, I made this slide a while ago, so this is from January 2011. If you go to the site today, you'll see similar sorts of numbers, but they don't show quite as much information, so it's not quite as interesting that you can get. But that was the RF requests for quotes that were out that day. So people put up on the website, I want you to build 10 of these little widgets for me. And then people bid on them and say, I'll build them for this much and I can do it in 48 hours, or I'll build it for that much and it's going to take me 72 hours. And then you get to some agreement, you say, okay, you got the job, and then they build it and it comes via Federal Express, and then you have this prototypes. And I've used it at MIT in my lab there, I've used it at my companies as a rapid prototyping service. There's a lot of machining, there's 3D printing, there's various prototyping processes. And you see over on the right there, from this particular day, some of the recent things. The third one is a government military buyer in Washington bought some stuff from a machine shop in Michigan. The next one is an automotive buyer in California bought some stuff from a machine shop in Florida, etc. And so a lot of the people who provide the services are little tiny 1- and 2-person companies, maybe high school graduates. They don't have degrees. They have a little machine shop, which previously had an addressable market of about 3 miles. And now they have a nationwide market. And how did this happen? Well, it happened because it's an invention, and some of this invention is a little old, but numerically controlled milling machines was important. And WYSIWYG CAD, I don't know what the age profile is here exactly. WYSIWYG, what you see is what you get. So, when you're using Microsoft Word, you see the stuff on the screen. If you're programming HTML, you're writing a programming language for what you get. So WYSIWYG CAD that you just draw and that's it. WYSIWYG CAD for metal parts, they're inventions that were needed, and these categories are a bit fuzzy, but the infrastructure that makes this work is that there's internet and web everywhere and PDF files, so you can send the design, you can put it up there. There's web payment services, because you have to pay for it somehow, so that infrastructure's there, and there's overnight shipping services. And then the business model, which I think 20 years ago would have been weird to us. You do anonymous bidding on this network thing and you don't know who's on the other side and you trust them. Well, there's certification through reputation in this thing, and we've gotten used to that with eBay. So there were business models that grew up, which then the MFG.com came in and glommed onto and makes it all work. So here's an example of a new mode of manufacturing. It's only for very small scale prototype, enabled by some inventions from infrastructure and some business models. What about Walmart class manufacturing? All the stuff we just buy, for our everyday lives. Can that be changed radically and empower smaller companies and smaller corporations to do useful stuff in it? So the coming industrial revolution I see is by a series of inventions, infrastructure, and business models. And it turns out this talk is going a lot faster than I thought. We're going to have a lot of time for questions. Oh, well, okay. So first, invent. What do we need to invent? And I've written down a bunch of things here that we need to invent. We need to really get beyond WYSIWYG CAD. And companies like Autodesk are going beyond WYSIWYG CAD for architectural sorts of stuff, but it hasn't really taken off where you can put in all sorts of constraints and get a class of models out and then optimize those models for various things. And the optimizations you need are maybe different metrics from just designing a part. If you've already got a running system, and you want to make some changes, you want to optimize the number of tools that you keep. You don't want to have to redo tools. So there's a different sort of optimization. And these things can get built over time. For Course 6 graduates here who are old enough, you might remember when the auto layout of boards, of PC boards, was so sucky that you could do it by hand and make it a lot better. Now, you use the program. The program's going to be better than you. So these things will, get better over time in terms of optimization. A lot of people think additive processes, 3D printing, is just going to solve everything. Well, 3D printing right now, you've got to move that little piece around, and so as the volume goes up, the linear dimension goes up. It's the cube of the linear dimension. Good printers work because you spray the whole one linear dimension on a page, so it's only the length of the page, not the area. But 3D printing is still the volume that you're printing. You can make stuff that you can't build other ways, but it's the volume, and so it's inherently slow. So trying to have a hologram sort of build the whole thing all at once is some invention that would help there. Or getting lots of materials together, and some people like Neil Gershenfeld are worrying about getting circuits built into the 3D printing. That's going to make things better. But there's a lot of invention there to be done. And then maybe, even if 3D printing is slow, if you could build a tool, a mold for an injection molded part out of a 3D printer, that would be a great innovation. You can afford the 3D printing of the tool to be slow, because then you can just pump out lots of them afterwards. And tooling is a big expense in any sort of mass production. And the third category I've got here is make automation simple to use. I was with someone from a big European company. I won't say their name. A big European automation company, and I was saying this idea, we should make automation tools, factory floor tools, easier to use. This is an old-time engineer who developed a really good product, mechanically fantastic product, and he sort of puffed up his chest and said, but machines are complex devices. So his self-worth was how hard it is to use machines. Now, these are really complicated machines. They're millions of times more complex than what we got people to the moon with. And yes, you can jailbreak this one, or if you just have a Android, you can type Unix commands to it to make phone calls, but that's not really very useful. So trying to make automation tools easy to use. And that's the one part here that I've been working on, and now I'm going to sort of show some stuff that my company, Rethink Robotics, has been doing. Industrial robots, and Vic Scheinman is here. Where's Vic? Vic, you're out there. I know you're there. Vic Scheinman. Vic Scheinman built the first electric 6 degree of freedom industrial robot in the world. Fantastic. It became the Puma. Fantastic history that Vic developed. But industrial robots are inherently still position controlled. They get very accurate at following a trajectory, and they're very good at doing it repeatedly, year after year after year. So that's the hammer that you've got, and you have to make your industrial process a nail that hammer can hit. And then, so you buy the robot, and then you buy cameras for them, and they're $7,000 a piece. Why are they $7,000 a piece? Oh, they're special cameras. Very special cameras. And you try and buy each piece of equipment, and it's sort of like buying a computer in the 1960s. You got to talk to various people and get a systems integrator to put them together, and you got to buy the pieces of software. So if you already have an industrial robot in your factory, the rule of thumb is 9 months to get a new process up. If you don't have one yet, 18 months, and the capital cost is only 20% of the cost of getting the robot running. And you better make it do the same thing for 6 to 12 months, or otherwise the cost of reprogramming it is horrible. So there are 300,000 small companies in the US with less than 500 production employees, almost none of which have industrial robots. So I wanted to get the barrier to entry way down, because that's what an industrial robot looks like on the left today, and it doesn't look very much like that thing on the right. So I started this company, Rethink Robots. Started to Rethink Robots. It was called Heartland Robotics originally. It's a very traditional VC-backed company, a lot of money with no before any revenue came in the door. So it's a big play, and we've just started shipping product. And the robot is the one on the right there. I hope you appreciate our logo in the top right-hand corner compared to the picture. That is a real guy in a real factory that uses the robot, but we did give him the orange shirt for the photo. But he was a perfect one to take a photo of. So the robot is called Baxter, and Baxter is a 2-arm, each arm is 7 degrees of freedom, force controlled, so it's not position controlled. In fact, it's not very good at getting to positions, but it's very good at applying forces. And we, as humans, do things through force control. If I have to slide my phone into this thing right now, and I was doing it with pure position, with no feedback, that would have to be very, very accurate to get it in there. But I use feedback, and I use compliance, and I can just slide it in. So humans use force control. If you're using force control, suddenly you have to sense force, so you can sense when you hit things, like people. Current industrial robots don't sense when they hit people. The servo loops just up the current and push their way through. It's not pretty. So this is an inherently safe robot with 2 7-degree of freedom arms and fairly simple grippers, because the technology for hands is not there yet. And you passively roll it around. And our aim, and this is what we have achieved often, is someone at the factory has never seen a robot before, a truck rolls up with a robot, 1 hour later, it's on the factory floor, put together by people who've never seen the robot, never seen the instructions, they've programmed it, they didn't know about how to program robots before, 1 hour, and it's up and doing useful work in the factory. So that's what we're after, and that's what we're managing to do. Here's it packing some gears off a conveyor into some boxes. It's very different from existing industrial robots. There's no integration. There's 5 cameras in the robot. It's a complete system out of the box. You just take it out of the box, you plug it into a wall socket. Doesn't take anything else. No programming, and I think Andrew referred to this earlier today. You train the robot. You don't program it. It's not about a sequence of positions. It's about the objects it's supposed to manipulate. You show it the objects it's supposed to manipulate. So it's not blindly going somewhere to grab the thing. It's looking for that part. So if the robot is moved or if the part moves, it goes and grabs it because it visually servos to it and then does a force sense on the grasp. So it's very quick to train it for simple tasks. Yada, yada, yada. This is the big one. No safety cages. One of the problems of putting a robot in a factory is you've got to have no people near it because it will kill people. But we have no safety cages. You just interact with the robot. You go up to it. You walk into its space. And Eric and Andrew are evidence that this works because they've been right in with this robot. And it sort of follows the computer model. You've got the hardware with software upgrades. The software upgrades give all the difficult stuff, all those error handling cases, all the knowledge of what sort of objects there are in the world. So in the early versions of the software that just understands conveyor belts. You don't have to tell it that there's going to be a brake beam and 0.34 seconds later you need to grasp. It just understands what a conveyor belt is, detects the motion, matches the speed, matches the direction. And that's in the early software. Later software we'll be bringing out over the next year, we'll know a whole lot about cardboard boxes. So you just put a cardboard box in front of it, it knows that's a cardboard box. So it's an intelligent system which has common sense about new classes of equipment over time. And when you program it, the screen that's its face puts a map up. Not when you program it, when you train it, you move its arm around. When you grab its arm, it goes into what's called zero force gravity compensated mode. And you don't even have to tell it that it's picking something up. If you bring the hand down and close the fingers around something and it feels it, it infers, that must be a pickup. And then it shows an icon that it's a pickup. So you don't have to even go through menus to make simple stuff. You can train it on visual stuff. Show it what an object looks like, etc. And so I'm going to show you a very simple training. This is actually going to be a blind one, just to show you how quick it is. So she grabs the arm, she presses a button on the cuff, the fingers feel there's something there, she moves it over there, she lets go. So this is a position-controlled version, this one, but that's getting it to pick stuff up and move it. So now, it's going to do that task. There better be an object where it was, where she told it would be, because it's blind at the moment. We'll add vision in a minute. It goes and picks up the object. It brings it over. The other arm realizes, I better get out of the way. So the other arm moves off a little bit. And then it realizes, the right arm realizes that the kinematic position wasn't optimal for where it was, so it re-figures out the right kinematics to use. So it's not just recording where you put it, it's optimizing the task. It saw that she was there, it gave a little puzzled look. When it's about to do something, its eyes glance over where it's going to be next. So if you come up to it, you know what it's going to do next. You can infer pretty easily without any training, knowing that it's about to move into your space. The screen's a bit washed out here, but this is just showing the screen with the same sort of training. It realized that was a pickup. It nodded its head to indicate it understood what she was trying to do. That's a put down. It understood what was going on there, and then it can do the task. Go back and say run, and off it goes to run. And it's always sensing forces. So puts it down, and actually it's so much more gentle than that now, realizes it's got it down, let's go. And she's in the way, but she's alive, she's alive. This is Mildred, she's from a plastics factory in Connecticut, injection molding factory in Connecticut. Who knew we had injection molding? Everyone thought they were all in China. Injection molding in Connecticut. She's worked in this factory for over 20 years. She's very typical of a factory worker in the US. Been working at the same place for a long time, aging, and hard to get new employees. That's an interesting thing. Everyone says, the robots are going to take the jobs. People don't want the jobs. People don't aspire to work in factories anymore. So what we're trying to do is make people like Mildred a supervisor of robots. This is 1 hour after she first saw a robot. She had already trained it to do a task in the factory. I don't know whether she has a high school diploma or not. We're trying to make it that easy to use, like our phones are easy to use. So we have a couple of slogans. It knows what you mean, it does what you want. And simple things should be simple to train, but you can go deeper if you want, and a manufacturing engineer can go in and tweak everything and optimize things if they want. Complex things are possible. So here's Noelle. You're going to see parts of her training, a more complex task here. The robot's sort of looking there. What am I supposed to do? What am I supposed to do? So she goes and shows it the object with the camera, and it learns the object. It moves around a little bit. It's got a range sensor, gets a model of the object. The production software that's shipping now has a slightly different interface, but similar to this. So she's now shown that right arm the objects it's supposed to pick up. The right arm, which is going to appear on the left of the screen. And it's looking around. It finally says, yeah, I got it. I really understand that object. It's ready to roll. So now there's a conveyor going here with these objects and other objects on it. Oh, it's still learning. Eventually it's going to say it's done. Yeah, I got it. It says check marks. And why do we have check marks? Not much language, because the people on the factory floor don't necessarily speak English, so we're trying to make it very iconic. So now that right arm is looking for those wide objects. It doesn't actually matter which direction the conveyor is going or what the speed is. Picks it up, and she had trained it to go and put them in an array in a box, in a 4x3 array. But there's other stuff on the conveyor there, and so she's going to show the left arm what to do about those. And she starts off, she doesn't actually do the pickup, she just gets it in the hand, and she's going to show what to do with it at the end. You don't have to train in order. The robot figures out what the order of things to do is, so that if a person is there doing half the task, the robot just opportunistically does the pieces of the task that haven't been done. So she brings it over here, the screen follows her around, it knows where she is, so she can see the screen, and she shows it to just drop whatever in its hand over there. Don't even put it down. She comes back and she puts out an area, look in this area for the object, and says, okay, I must have to pick this up here, but I still don't know what the object is that I'm supposed to pick up. So she's going to go in and add the eye icon and show it this new object, this rubber ducky. It's going to go build a model of that and then be able to see those. And now, on the right of our screen is the left hand. It's looking for rubber duckies. On the left of the screen is the right hand. It's looking for these white widgets. And the hands are going to pick up and sort the objects to where they're going to be. Here comes this left hand. It sees the duck. It goes down to pick it up. Missed. So it tries again. It realizes whether it succeeds at things. You don't have to put that logic in the program of what to do on failure. That's all built in. And off it goes and does the appropriate thing with the rubber duck, which is let it go for a swim. Now, I said grippers are hard. So we've tried to. This is an early video. But we've tried to make it so that ordinary people can build robot hands on the fly, and we've adopted an IKEA model. Now, some people groan about IKEA, but you get a gripper. There's pneumatic grippers. Third parties can build them. You get a gripper kit. You take out the and again, not a great video because not all the parts are in the box right now. But you take out these instructions. This is the electric element of the gripper. She's going to screw it in with a couple of little hex bolts. Oh, I'm not going to run out of time. I'm not going to be early. I'm going to run out of time because I've been showing you so many videos. Oh well. She puts it in. She plugs it in. Immediately says, I see. There's a gripper there. Now she goes and says, okay, I'm going to pick up this rubber ducky. Figures out what fingers to use. She gets them out of the finger kit. She installs them. So that sort of gives her instructions on how far apart they are. So you don't have to be a manufacturing engineer to figure out how to pick up your object and how to optimize your hand for the object. And then you can put various sorts of rubber elements on there and stoppers on there. But there's one little problem. These fingers are visible to the camera in the wrist, which is also trying to see the object. So now, how do you tell the robot, especially if you build a custom hand, how do you tell the robot what the hand looks like as distinct from what the objects look like, and how do you deal with that? So you press the train button, ultimately here, and in a second she's going to click on the train icon, and it brings the hand up. There's a camera in the top of its head there. Oh, well, no, actually it's using the camera in the wrist, but the screen is putting a background against which it can see the fingers, and it builds a visual model of the fingers in real time, and now knows what the fingers look like. So you don't have to give it a CAD model of the fingers. Okay, so I'm going to skip there. $22,000 made in the US for this robot, unbelievably cheap. I'm not going to have time to talk about why we can do it, but the point is it's made in 19 locations across the US, integrated in 4 manufacturing sites into a final assembly in New Hampshire. By carefully designing things, you can build cheap stuff, great stuff in the US. And this is really important to our customers, that these robots are built here in the US. So that's an example of the sorts of invention we need. We also need new infrastructure. This is Flextronics saying they can just put up a new plant in 90 days in Asia with 5,000 employees. We can't do that in the US. So we need all sorts of infrastructure to allow that. Scalable, fast setup factories, new standards of plug-and-play equipment, tooling capability. I think there's new sorts of B2B Amazon-type plays that no one's using right now for supplying the sort of supply chains that you need to build things like 40 million cell phones every 3 months, if Apple was to do this in the US. A lot of infrastructure that can be built. And business models, I'm not going to go into a lot of detail here, but I think right now, someone who develops a product is the person who is the entity which controls the manufacture of the product, and then it goes off to channel to retailers. Once you get enough CAD, which the CAD is parametric and understands the manufacturing process, there's no need anymore for the people who develop it to also be part of the manufacturing process. So now you get to sell this much more rich design, and the people who are the retailers can contract out and manufacture locally close to the point of sale. And then you see this whole analogy where software used to be an object you sold, and then it became a service. So maybe there's a software as a service, objects as a service. There's all sorts of possibilities there, which I think will lead to Industrial Revolution 3.0. And I've got 4 seconds left. No time for questions. I apologize, but thank you.